Okay, so in this video, we're going to look at secant and tangent lines. We're going to continue to build our way into an understanding as to what the derivative is, and we kind of hinted at that in the last video. So a secant line is a line that intersects the curve at 2 points, and we use that line by finding its average rate of change, which would give us the average rate of change of a function over the interval by finding the change in y over the change in x. And just from a notational standpoint, if I had an x value of a and an x value of b, and I wanted to find its average rate of change, y2 minus y1 over x2 minus x1 would be f of b minus f of a, that's my numerator, over the overall width of the interval, or the distance between the x values, b minus a. And if we wanted to, and that wouldn't give us the instantaneous rate of change of the function, it would just give us the average rate of change over an interval. The tangent line, on the other hand, is a line that touches the function at only 1 point locally. Now, a tangent line could intersect the function somewhere else outside of a small window. However, at or around this point of tangency, it will only touch the curve in one time. And in fact, at this 1 point here, the tangent line and the curve are going to have identical slopes. And that takes us to our next stage in terms of how do I find the slope of this tangent line if I'm only looking at 1 point, because our average rate of change formula requires us to know 2 points. And also remember that this point of tangency, in order for me to do this process, we have to be locally linear, and we talked about that in the previous video as well. And so, okay, so let's look at a graph here, and my green line is my tangent line to the curve of this parabola, and the point of tangency is at 3 by 54. Now, what I want you to notice is, look at what happens as I start to zoom in to this point of tangency. Notice how the closer I get to this point, in terms of the more zoomed in I get, the harder it is to distinguish between the tangent line and the curve. In fact, if I zoom in a tremendous amount in a very tiny window, you can't tell the difference between the two. And so around the point of tangency, the tangent line and the function are going to produce very similar y values, and they're going to have the same slopes. And so to summarize what I just said, around the point of tangency, the tangent line and the function will have similar output values, similar y values, and the slope of the tangent line will equal the slope of the curve at the point of tangency. Okay, so now we're going to look at the relationship that exists between the slope of a secant line and the slope of a tangent line. And we went through this process at the very beginning, the first video of this chapter, when we're trying to predict the instantaneous rate of change of the thrown ball at a given time interval. And so what you're looking at here is I have 2 points that lie on the curve, and one of the points is they have in common, and that's the 3, 54 in terms of the curve, the secant line in red, and the tangent line in green. And what I want you to notice is, currently compare the slope of the green and the red line, so the tangent line and the secant line. Notice how they're not similar at all, but notice how the secant line is dependent upon whatever the second point is that I choose. Now watch what happens to this, to the secant line and the tangent line as I move that point closer to the point of tangency. So the closer I move that point to the point of tangency, the more similar the secant line and the tangent line get. So in fact, if I start really closing down this interval and I pick points that are really close to the point of tangency for the secant line, they will start to become almost the same line. So if I were to drag this point almost all the way there to 3, not quite there, and I zoom back out, notice how you really can't tell the difference between the tangent line and the secant line. And so to summarize that, as the distance between the 2 points used to create the secant line approaches 0, the secant line will wind up becoming the tangent line. Now, that is a very important idea there, or a concept there, in terms of as I close down this interval for the average rate of change or the slope of the secant line, and how it becomes the tangent line when this interval becomes zero, has a width of 0. That brings us into being able to create a limit to determine what the actual slope is of the tangent line. And we have two options to go through this process. The first option, which are limits that are represented by using h, which h represents the width of the interval. So if I'm looking here on the left-hand side, I have 2 points that lie on the curve, and I have at x equals a and x equals b, and the distance between a and b are going to be h. So we're going to define these points as x equals a and a plus h. Now, my secant line at those points would have a slope of y2, which is f of a plus h, minus y1, which would just be f of a, over the difference in their x values, which would be x2 minus x1, so a plus h minus a. And if I condense that down and simplify it, I get this here for my secant line slope. Well, in order for us to look at or predict what the slope of the tangent line is, what I would have to do is find the limit as h approaches 0, so the width of that subinterval approaches 0, for my average rate of change. And this limit here is the slope of the tangent line, but it's also equal to the derivative at that point. And that point in this case would be at x equals a, so f prime of a. And that's how you represent the derivative and the slope of the tangent line. Option 2 was going to be written in terms of as x approaches a certain value. So I'm going to use the same graph. I'm going to look at it slightly different. So I'm going to have a point that is x equals c and the y value is f of c. And I have another point, call it x, and its y value is f of x. And so my secant line between those 2 points would have a slope y2 minus y1 over x2 minus x1, f of x minus f of c over x minus c. Now, our tangent line to the curve at x equals c in this case would be the limit of that slope, which would be the limit as x approaches whatever c is, whatever that c value is, as x gets closer and closer to that value. The slope of that tangent line is going to equal f of x minus f of c over x minus c. So that would be the slope of my tangent line at x equals c, or f prime of c representing the derivative. And those are two very important limits to keep in mind as we proceed forward. Okay, let's do some examples here, finding average rate of change and looking at finding the slope of some tangent lines. So this first part, we want to find the average rate of change of f, and we're given this function here over the interval from 1 to 3. So the average rate of change is going to be equal to f of 3 minus f of 1, so y2 minus y1 over x2 minus x1. And so all I need to do is figure out what those y values are. And so basically we're just getting their y values. So we should get f of 3 to be 10 and f of 1 to be 0. And then we're going to put back in to our slope formula, our average rate of change function. And we have 10 minus 0 over 3 minus 1. So the average rate of change of the function over that interval is 10/3. Now, for the function f of x is equal to x squared plus 9, we want to find the slope of the secant line here between x is -4 and x is equal to -1. Well, the slope of the secant line is the average rate of change. So the average rate of change over this interval would be f of -1 minus f of -4, so y2 minus y1 over x2 minus x1. So I just need to plug in and get their y value. So f of negative 1 gives me 10. F of negative 4 gives me 25. And then I put this back in. So I have 10 minus 25 over negative 1 minus negative 4 gives me negative 15 over 3. So the average rate of change of the function over that interval is negative 5. Okay, now let's look at an example where we want to find the slope of the tangent line at x equals negative 4. Now we have two options for how to approach this. And what we're going to do is we're going to do one problem using each option here, so that way you kind of see it. So the slope of the tangent line at x equals negative 4, that's going to be f prime of negative 4. And I want to know what that's going to equal. Well, to do this, we're going to have to do a limit. And so the limit that I'm going to use is the limit that says that f prime of a, so the slope of the tangent line at a, or the value of the derivative of the function at a, is going to equal the limit as h approaches 0 of f of a plus h minus f of a over h. So f of negative 4 is negative 138. And I also need to find f of a plus h.
So I got to put that into my problem.
And then I got to simplify this because it's going to make life a little easier as when we go to do our limit. And so we combine like terms right here, and what we get is negative 8h squared plus 68h minus 138. And so we know what f of a plus h is, in this case negative 4 plus h, and we know f of negative 4 is equal to negative 138. So what we're looking for is going to be the limit as h approaches 0 of f of negative 4 plus h minus f of negative 4 over h. All right, so we're going to plug in our expressions. So we have the limit as h approaches 0 of negative 8h squared plus 68h minus 138 minus negative 138 all over h. And what we're going to be left with is the limit as h approaches 0. We'd have negative 8h squared plus 68h over h. My h's are going to cancel out. And I could rewrite as the limit as h approaches 0 of negative 8h plus 68. Then put in 0 for h, and we get 68. So 68 is the slope of the tangent line at x equals negative 4. Or actually, we want to find the equation of the tangent line at x equals 2. Well, in order to find the equation of the tangent line, I need to find the slope of the tangent line. And we're going to find the slope of the tangent line using a different limit here. You're going to use the fact that the slope of the tangent line at x is equal to c would be equal to the limit as x approaches c for f of x minus f of c over x minus c. So we're going to go this route. F prime of 2 would equal the limit as x approaches 2 for my equation, so 10x squared plus 10x minus 1 minus f of c. F of c would be put in 2 to my function and see what I get. So f of 2 is 59. And then So that over x minus 2. And then we work to simplify from here. Okay, so we factor it, and we end up with 10 times x plus 3 times x minus 2 over x minus 2. And I'm going to come up here, and I'm going to continue to simplify so that way I can evaluate this limit. And so it'd be the limit as x approaches 2 of 10 times x plus 3. Now I can finally put 2 in, and that gives me 50. So 50 is the slope of the tangent line at x is equal to 2. Well, to write the equation of the tangent line is going to be, what I can do is I can say y equals whatever the function's value is at 2, because it passes through that point, plus the slope of the tangent line times x minus the x value. And so all I got to do is put my values in. So y equals 59 plus 50 times x minus 2. And I'm going to leave it just like that. Now, since we defined the slope of the tangent line as a limit, we have to keep in mind that there are limits that don't exist because of either some kind of discontinuity or vertical asymptote or an oscillating function. And it's often helpful to be able to look at a graph and be able to determine if they're vertical or horizontal tangents. And so for this next example, we're just going to look for where will the graph have a vertical tangent line. And the graph on the far left here, if I'm looking at where would I have a vertical tangent line? Well, this curve goes from -2 to +2, and it's the top half of a semicircle. And right at that point of that semicircle, the far left and the far right edges here, we would have vertical tangents. So we'd have a vertical tangent at x equals -2 and at x equals +2. The next graph, if I'm looking at it, this looks like the graph of maybe the cubed root of x or something very similar to that. I'm looking for where the graph gets vertical. And in order for it to have vertical tangent, well, look right there at its point of inflection, in this case at the origin. That tangent line right there at the origin for that tiny little space would be undefined in terms of its slope. It'd be vertical. So we would have a vertical tangent line in this problem at x is equal to 0. Now, this isn't the case for all of these kinds of functions, but we're just being able to look at the graph and try to figure out where the vertical tangent might be. And another example here is in this third graph. I look at it. Now, I see a sharp turn right here at the origin, and we know that sharp turn is where the function is not locally linear, but also the graphs here on these two ends. As you approach the left and the right side of that, they are both bending and becoming vertical there. So there's actually going to be a vertical tangent line at x is equal to 0. And so one more graph here, we're going to expand and look at more than just vertical and horizontal tangents. I want to say and look at a graph and determine where will the graph have a horizontal tangent, a vertical tangent, or where will the tangent line be non-existent. And so let's start with horizontal. Horizontal tangent line is going to be where the graph really starts to flatten out. We're going to look from -9 is less than x to +9. So we're not going to really look at any of the endpoints here. Well, to do this, we're going to kind of zoom in, and I can see the graph at -3 appears it would have a horizontal tangent line there at -3. And it also appears that it flattens out at +3, like it would have a horizontal tangent line right there at that x value as well. So we have horizontal tangent lines at -3 for an x value and +3. for an x value. Now let's try to find vertical tangent lines. So vertical tangent line, where does the graph appear to be vertical at? Now, the tangent line itself, I'm looking along the graph, and I see at x is equal to 0, right in this range, is where the graph, if I drew a tangent line right there at that point, at 0, -2, the line tangent to it would be vertical. So at x is equal to 0, we would have a vertical tangent. Now, the next question that we have is where would the tangent line be non-existent? Well, the tangent line will be non-existent at two places. It'll be non-existent at a discontinuity, x is equal to 6, and also where it's not locally linear, so I see that sharp turn at x is equal to -6. Okay, so now let's go find the slope of the tangent line at the indicated points. And the method that you use, what limit you use is up to you. That part doesn't really matter. Now, the good thing is we're going to look at the same function each time. So f of x is equal to x squared. So whatever limit I choose to use for this, to find the slope of my tangent line, I'm just going to have to do the hard work once and then just change the x values I'm going to plug in. So I'm going to use the limit that would give me the value of the derivative at a, or the slope of the tangent line of a, being the limit as h approaches 0 of f of a plus h minus f of a over h. So that's the limit I'm going to use. Now, I need to figure out what f of a is, and I need to figure out what f of a plus h is. So f of a, well, a is 0 in this problem, so we're really looking for f prime of 0. So f of 0 is 0. F of 0 plus h is just going to equal, f prime of 0 is going to equal the limit as h approaches 0 of h squared minus 0 over h, which is going to be the limit as h approaches 0 of h, which just gives me 0. So the value of the slope of the tangent line at 0 for this curve is 0 itself, which if I think about it, that means I have a horizontal tangent line at x is equal to 0. Now let's do it again looking at x is equal to 1. So I need to know f of 1, which would be 1. I need to know f of 1 plus h, which means I have to do 1 plus h and square it. That's going to give me 1 plus 2h plus h squared. And now I can go back into my limit and plug all this back in. So f prime of 1, so my tangent line at x is equal to 1, is going to equal the limit as h approaches 0 of 1 plus 2h plus h squared minus f of 1, which is 1 over h. And I simplify, which would be 2h plus h squared over h, which is going to make the limit as h approaches 0 of 2 plus h. And I put 0 in, and we get the slope of the tangent line at 1 to equal 2. And the slope of the tangent line at x is equal to 2. So I'm using that same limit definition that we have to find the slope of a tangent line. So I need to know what the y value is at 2, which is 4. I need to know what do I get when I put in 2 plus h. Now I know I'm going to square that, so I'm going to go ahead and expand it. That makes 4 plus 4h plus h squared. And then I'm going to put this into my limit. So f prime of 2 is going to equal the limit as h approaches 0 of 4 plus 4h plus h squared minus 4 over h, and simplify that limit so I can evaluate it. So that'd be 4h plus h squared over h for my limit, and that would simplify to the limit as h approaches 0 of 4 plus h, and that's going to give me just 4, which would be the slope of my tangent line at 2, or f prime of 2. Now, you might be thinking to yourself, is there a way we can generalize this and speed this up so that way we can get an equation that would tell us the slope at any point if we were to just plug in? And the answer to this is yes. And what we're going to do is, let me pull up Desmos, so we're going to look. And so I have a table that is plotting the same derivative values that we just found for f at x is equal to 0, 2, and 4, or the slope of the tangent line there. And if I connect those points there, what you'll see is there's actually, we can create a derivative function. And along this function will give me the slope of the curve on y is equal to f of x at any x value. So if I could figure out the equation for that derivative line, or that derivative function there in red, I could immediately get what the slope of the tangent line would be on my blue curve for any given x value. And so that takes us to the limit definition of the derivative, which is basically the same definition that we had, except for instead of using an x value, we had a right there, we're just going to use x. And when we complete this limit, we're going to be left with an equation that will allow me to get the derivative at any point.